Good try, though. Okay, draw y equals x squared on the axis below. Pick a point on the curve and label it pxy. Okay, let's do that. Draw the line y equals 1. Okay. And find the distance d from the point P to the line. I'm going to argue that it's this distance. Find that distance, please. Oh, it's -1, yeah. What's the distance? Yeah. It's just y minus 1, is it not? Folks. Hello? Can I just drill a hole in my head right now? Draw the line y equals 4 and find the distance from D to the point P, from the point P to the line. Well, I guess this one, it'll depend on where you... Because it could be 4 minus y, or y minus 4, depending on where you put that point. Okay. I'll draw the line x equals minus 1 and find the distance for d from the point P to the line. Why? I don't want to. Whatever. Okay, we'll do it. Isn't it just going to be x plus 1? And the line x equals 3, it would be... Yeah, whatever. You know what? Whatever. Okay, we need to know some... Today, I'm looking at this going, I don't quite need to do quite... We did this. Like, I'm like, why are we reviewing this so much as we did? So, area of a circle. Thank you. Semicircle. Square. Or length squared, or width squared, or side squared, or whatever you want. Isosceles right triangle. One half x squared. An isosceles triangle is just half a square. Since always. Probably never said that like that to you in grade 8, but okay, equilateral triangle. So what we need to do here, this is where you're going to have to do a little bit of thinking. If this distance is x and this distance is half x, no, we got to pi over... No, it's half a parallelogram. No, it's too much work. So, shh. No, it's a rectangle then. It's two right triangles. Yeah, I was just... No. It's not isosceles. He's equilateral. Equilateral, 3 equal sides. What I was attempting to do when you guys were yelling at me was to put pi over 3 down here, 60 degrees, right? And then I was going to ask you to use that whole thing that you learned in Math 10. So if that distance is x, and that's half that, like, look at the relationship. If you divide that by 2, you divide that by 2, you divide that by 2. So this is root 3 over 2x. So how do you find the area of that triangle? That height, the height is root 3 over 2x. So the area of the triangle is base times height divided by 2. Base is x. Height is root 3 over 2x. And divided by 2. So it's going to be... No, this whole triangle. X squared, root 3x squared over 4 is actually the area of that triangle. Root 3x squared over 4. Two times 2. That 2 drops down into the denominator when you simplify. If you multiply by a fancy form of 1, that's what happens. But anyways. Okay. So consider solids we have been working with. Suppose we sliced a solid and pulled a cross-section. Okay, so what I did a couple of nights ago is I went online and I went and found some videos that illustrate this idea, what I've been we're going to talk about now. So the first one is somebody's taking a curve and so they draw area. We know how to do that. Okay. So what we're talking about now is building semicircles on the top of the that shaded area to create a volume. Okay, but notice. Oh, no, I'm going to talk about. Maybe we'll let it run for a little bit more. So this is using semicircles. And it creates a curved shape, and you can find its volume. You can change it to triangles and do the same thing. I'll tell you what shape I want you to use. Just watch. Yeah. And then rectangle. Because shapes are circles, not all shapes are triangles, not all shapes are squares. Hey, look, it's a pyramid, sort of. Okay. So, what we need to do is volume formula. How could this formula be cross-sectional area? So what we need to visualize, and this is the shape that we're talking about, so we have some general shape. And that'll be f of x, g of x. No, I'm just asking you to think along with me. If we're going to build squares along this side, so, yeah, I know I can't draw, but whatever. We're going to build squares. And this side defines the length of the square. How do I talk about the volume of this piece of wafer? Length. Okay, length times width times height. What's the length? Say that the other way around and you're right. Yeah, f of x minus, kind of, but we want to just do it this way, and then we'll do what you're suggesting. Width, this distance. And then height, that's this distance. That's dx. And then how do we find it? Well, we integrate from A to B. Just with changing, all we're doing is changing the formulas. But what if, okay, instead of building a rectangle, I build a circle. Or a cylinder, actually. Yeah, I know I can't draw. So, it's going to be the integral from A to B, and then how do we find out the area of a circle, or half a circle? Call that distance D, right? Because it's the diameter. So it's going to be f of x minus g of x, that's the diameter, over 2, so that's r, pi r squared. Yeah. Well, yeah, divide by 2 again. And then we could do a triangular prism, the equilateral triangle. Yeah, no, it'd be over 8, because it'd be squared, or 2, 2, 2. So if we did if we did an equilateral triangle, it'd be the integral from A to B of, what was the formula that we made for the area of an equilateral triangle? Root 3 over 2x squared. Root 3 over 4. Yeah, but what's x? X is this distance. F of x minus g of x squared. Yeah. It's on the AP exam. Sorry. Well, I mean, sure, you can always, especially with circles, semicircles, to find volumes of weird shapes. Yeah, it's new, it's creative, it's on the exam. Yeah. You want to see it again? Do you want to see the video again or no? Okay, consider the solids we've been working with. Shh. Folks, did we answer this question? Consider the solids we've been working with up to this point. Suppose we sliced the solid and pulled out a cross section. What would it look like? That was those videos I showed you. Look at the volume formula. How could this volume change in terms of its cross-sectional area? Did we just do that together? That was, yeah, the top one, the only one you can access. No, the other one doesn't. Yeah. Consider another type of solid. This solid is not rotation about a line. We've done this. Can you imagine a solid having a cross-sectional base? We've already done all this. Flip the page. So, find the volume of the solid where the base is a circle. So, I would like everybody to draw me a circle with a radius of 3, please. Everybody should be able to look at that and say, hey, that's a circle with a radius of 3. Like this. Shh, there. The cross-sectional area perpendicular to the x-axis is an isosceles right triangle with one leg in the plane of the base. Okay, so what we're going to do is we're going to attempt to draw without embarrassing ourselves too much. Draw a little line, and then attempt to draw a right triangle that uses that as its base. Make it 3D. Maybe we should have somebody from the art class come over and do it for us. We do. That's what I'm saying. And how's that? Is that good enough? Mr. App, it's not good enough, but that's all right. So we want to... I know it's terrible. We could all pitch in. Well, you could draw that. So, find the volume, blah, 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 blah. So we're going to go from here all the way over to here. And we're going to build triangles, just like the video showed us, and we're going to stack them. Well, let's write what the integral is, though. We need to write out what the integral is. So we need to start, we're going to start at -3, because that's the coordinate of that point. And we're going to go over to the other coordinate. Now what we need to do is to figure out the distance, this distance. How are we going to figure that out? Come on now. Y equals plus or minus the root of 9 minus x squared. What's the top function's equation? What's the bottom function's equation? Exactly. So how are we going to find that yellow distance? How do you find that distance between the two arrows? F of x minus g of x. So all we need to do now here is put the volume. We need to put the volume of that triangular shape, or the area. What's the area of that triangular shape? What? What's the formula for an isosceles triangle? 1/2 x squared. Now x is the distance between the two curves. So it's going to be 1/2. What's x squared though? Thanks. Root 9 minus x squared minus negative root 9. Yeah. And then you can clean this up. F of x minus g of x. Take the half out front, Mr. App. The minus is a plus. Well said. 2 root 9 minus x squared dx. Square the 2. 4 over 2 root negative 3 to 3. What happens to the square root? So it's not a hard antiderivative if you're willing to do some algebra to clean it up. Yeah? So it's 2 open big square bracket 9x minus 1/3 x cubed from -3 to +3, and that will give you the area. You can finish it from there. You know what? Okay. So now we're going to make it an equilateral triangle. So draw the shape again. Hopefully you guys are going to notice Mr. Epp is the same as always. The only thing that's changing is the formula that you're working with. So draw a circle again, laugh at me, pick a random point. Make it 3D, or attempt to make it 3D. This is pretty good for me, by the way. Grab the area formula that we've been talking about. So it's 3√3/4 distance squared. And you've already done all the work for that. It's just that, so 9 minus x squared minus -9 minus x squared dx. Do you want me to continue the cleanup process and say this is what it looks like when you're finished? Yeah, but yeah. I don't know. Talk to Mrs. Corey. Yeah, there is. It's not. It's like the root of a plus b times. Yeah, you don't want to know. There is. You can look it up. Yeah. Okay. Oh wait, I wasn't finished that. So you square the 2, you get 4. The square and the square root cancel. He shouldn't lean in with his face into somebody's elbow by the looks of it.
I mean, he needed to improve his left ankle instead of
No. Okay. Anyways, 4's cancel. So you're left with √3 integral. Yeah, whatever. -3 to 3 of 9 minus x squared dx. And you can finish it off from there. Yeah? Hard? No. I think the tough part is going to be remembering what formula. How do I find the area of the triangle? It's the. Okay, so find the volume of the solid where the base of the region. Okay, so y equals sine x. We could draw that. Yoink. And the x-axis between x equals 0 and x equals pi. Good, that's all I needed to do. And the cross-sectional area is a square. So we'll draw a square on the cross-section. So we'll say, okay, Mr. Epp, there's the shape. And we're going to build squares off of that. Yeah, I know. Whatever. You get the idea. Don't laugh at me. It hurts my feelings. So we're going to integrate from 0 to pi. And that's sine x. And that's sine x. There's no f of... I guess you could do f of x minus g of x here, but it'd be like sine x minus 0. Yeah? Because the bottom line is on the x-axis, sine x minus 0. But like, so the area of a square is length times width. So sine x times sine x, or sine x minus 0 times sine x minus 0. I really don't want to do this, but can I just do this then? dx. This doesn't antiderivatize very well, so we'll use our calculator. Just put it in y1. So the volume of the squares on the side are 1.5707900963. 1.57070963. I think that's pi over 2 if you want to check. Yeah. Yeah. So it's just, you just got to look at, I mean, all we're coming down to, what this is all coming down to is what is the distance of the side of the shape that we know, and then use that as your x in your formula from the previous page, and you just substitute it in and use it. Because x isn't an x coordinate. X is the distance, or the length of that side of that shape that you know. So maybe we should go back and change all of our x's on our previous page to something else, so we don't use the letter x, so we don't think about that. But we want to call it d for distance. You know what I mean? Like, or are we okay with using x on our previous page? Well, it's not finding, it's finding the area of all of the squares. It's building rectangles, an infinite amount of rectangles of different size, and stacking them up. That's what you have to visualize here. Yeah. The formula is just different, though. Yeah. I can't draw, but yeah. Well, we kind of saw the video of the shape. But, you know, what happens when you stack, it's kind of like a pyramid, kind of. A weird pyramid. Is a semicircle, okay. I can't draw. So we're building little half cans. Somebody actually draws this somewhere. I was going to YouTube it. Nah, whatever. So it's going to be the integral from 0 to pi. Now, you got to remember how the difference. Okay, so area of circles or semicircles can be written as pi r squared over 2, or the one that most kids don't know, pi d over 2 squared. So you can convert that. Diameter is half the diameter is the radius. It's not, it's a 2. Sorry. Pi d squared over 8. That's probably a better one to use for this. Because d is the distance. This is d. All of that, right? So all of that distance is sine x. Pi over 8 d squared weird? I'm getting a weird look, but weird, yeah. I'm gonna stop something at the end. I'm gonna say, hey, take a look at this. This is something that probably never even noticed before. when you learned area shape formulas. But you know what? Let's do it right now. I want to do this right now. Okay, get a piece of scrap paper out or flip to the inside cover, their last cover of your book. Last page, inside cover of your green book, draw these shapes. You got that blank green page there? There's a blank white page? Okay, put it there. I don't care. Oh, just... Okay. I am filming it. So we're calling this D, distance D. So the area of that shape is D squared, yes? What's the area of this shape? If that distance is D, pi r squared. Pi pi over 4d squared. Area of this shape is exactly 1/2 of the area of the other shape. Pi over 8d squared. I don't know if it's anything profound. An isosceles right triangle. 1/2 d squared. And then the weird one, the equilateral triangle, √3 over 4d squared. What is the same about every single one of these formulas? D squared. What's the only thing that's changing? Yeah, the coefficient. So all you don't really have to memorize formulas. All you really have to do is memorize coefficients. A square is 1. A circle is pi over 4. A semicircle is pi over 8. A right triangle is 1 over 2. An isosceles, an equilateral triangle is √3 over 4. They're all d squared. Math 8. That's why it is. You know, it's all the area formulas from before. But it's why are they all squared? Because area is 2 dimensions, a length and a width being multiplied together. A unit centimeter times a unit centimeter is centimeter squared. So all it is just the coefficient is changing. Don't you dare say that to a grade 8. They'll probably cry in the corner. Yeah. Find the volume of the solid where the base is y equals e to the x, y equals e to the negative x, and the line x equals ln2. Y equals e to the x. Y equals e to the negative x. And when the line y equals x equals ln2. I don't know, ln2 is right about here. So what area are we talking about? We're talking about this area here, and we're going to build, what are we going to build on it? It's a square. Building squares on a curvy triangle. So we're going to integrate from 0 to ln2, from 0 to ln2, of d squared. Oh, just a sec. What's the formula that we just drew on our... Oh, it's d squared. And d is... There they go. Throw in your graphing calculator. Second trace 7. Do you want me to finish that on the calculator just so you know what the answer is? Because d is the distance between the two between the two curves. F of x minus g of x. The higher minus the lower. Are you guys deliberately annoying me today, or are you just practicing it? No, I'm just about done with you. One more bracket, squared. Second trace. I don't even care what the graph looks like. Second trace 7. Zero, enter ln2. The volume is 0.4887. Yeah? 0.48870. Okay, what? Okay, good. Start to recognize how much, if you know the square answer, you know all the other ones. There you go. Yep. So, which coordinates? They're representing the volumes. They're representing the volume. That answer of 0.48870 is the volume, not the area. The area under the curve represents the volume of the shape. What? Yeah, or the volume. The coordinates of the volume here. The area under the curve of the function we just graphed represents the volume of the shapes if we add them up. No, I'm not saying that. No. I've never thought about it. I have to think about what the coordinates mean. Cross-sectional area to the 6. So I guess we could put the formula here as just pi over 8, 0 to ln2, e to the x minus e to the minus x squared dx. Riley, ND? Yeah. So it's just pi over 8 times 0.48870. And we're doing this. Good. Find the volume of an object that lies within 2 and 5 and its cross-section of the point is the length of square x. What? You know what? Fine. Find the volume of an object that lies within 2, 5. So 2 and 5. And its cross-section at each point, the length of the square is x. So what we're saying is no matter what I draw here, the distance is always x. So you're just going to integrate from 2 to 5 x squared dx. Yeah. This is kind of what we've already done in our notes. This is kind of funny because I'm generating stuff that's, I'm getting ahead of myself. This page back here does it all for you. No, not rotation. No rotation required. Good job. So find the volume of an object that lies between 0 and pi over 2, and its cross-section is a length of square with length cos x. So we're saying this distance is cos x. Actually, we're not even saying that. We're saying we've got a shape that follows cos x. We're saying the distance between the two curves is cos x. So they're telling you, what this is saying is f of x minus g of x is cos x. So somebody's done all this algebra for you and simplified it down to say the distance is cos x. So the volume of the square, so it's going to be the integral from 0 to pi over 2 of cos x squared dx. That makes sense? Do you want another one like that, or? Okay.